So, welcome back to the course on architectural design of ICs. So, in the last few classes we are seeing algorithm to efficient architecture mapping techniques. There are several tricks and tips for that means techniques for designing the efficient architecture from different one particular algorithm that can be implemented in different way in considering speed or power or area as a major constant. So, we have seen few of the examples how we can design them, okay, considering different aspects. Okay. So, in the last class we have seen that one architecture of y equals to, suppose I have to implement one function that is y equals to 2 to the power x plus 1. So, at that time what will be its architecture? If that initially we have started from designing this y equals to 2 to the power x function, then we have just started designing another function which will be implemented from that particular point, that is y equals to 2 to the power x plus 1. And in the last class I have just ended with that. Okay, so, we have seen that I can design 2 to the power x plus 1. So, from that particular point can I design 2 to the power x plus 2, 2 to the power x plus 4, 2 to the power x plus 8. So, if I can design, then how can I design? What will be the techniques or tips for designing them? Okay. So, we will see that. So, in the last class what we have seen, so we have seen y equals to 2 to the power x plus 1 in the last class, right. So, whenever we have designed this 2 to the power x plus 1, at that time how we have designed? So, initially what we do? So, considering x equals to of 4 bit. Okay. So, how we have designed? So, initially we have plotted like this x 3, x 2, x 1 and x 0, and for that what will be this 2 to the power x value, and then we have to find out this 2 to the power x plus 1. And after getting this operation table, okay, of this particular circuit, then we have find out the corresponding each of this expression, that means each of these bit positions, what will be the logical expression for that. So, after finding this logical expression for each of these bits, then we have just mapped that logical expression into architecture. So, whenever we have designed this 2 to the power x plus 1, so at that time what we have seen? We have seen that there is only change in these two particular position, rest of the positions are remain same. That means, as I am adding only 1 at the LSB position, so that is why it is affecting this LSB bits of this 2 to the power x and the corresponding bit which is just adjacent to this LSB, that means next to the LSB. Why? Because this carry is basically affecting the corresponding bit, and then why it is not traversing to the other MSB side? Because in 2 to the power x, how we are getting it is we are getting this, that means output like 1 0, then 4, then 8, something like this. So, as this only one of this bit is 1, rest of the bit is 0. So, that is why it is not affecting the corresponding other bit. That means, the carry is basically diminishes at this particular second, that means adjacent to this LSB position. It is not traversing or it is not affecting the other bits, that we have seen in the last class. Now, consider instead of this 2 to the power x plus 1, okay, now here I need 2 to the power x plus 2. So, at that time what it will be, or how I can implement the circuit, that is 2 to the power x plus 2, or where will be the change, or how, what I need to change so that this circuit implement 2 to the power x plus 2 function. Okay. So, let us consider these things. I have to implement 2 to the power x plus 2. Okay. So, for that again what I have to do? So, we know that, okay, we know that this is x 3, x 2, x 1 and x 0. Okay. So, for 2 to the power x, it will be something like this 1, then Okay, let us consider this 0 1, then 0 0 1 0 2, then 4, then 8, then 16, something like this I will get, okay, for 2 to the power x. Now, what I need to do, that is 2 to the power x plus 2. So, 2 to the power x plus 2 if I want to design. So, at that time if I just add it with 2, so at that time what it will be? It will be like 1 1, it will become 3, then it will become 2 to the power x 1, then with 2 if I just add, then it will become 4. After that it will become, this 4 will become what? 6. 4 plus 2, that is 6. So, 10 will become 12, sorry, this is 8, 8 will become 10, then 16 will become 18. Okay. So, that means this. So, if you see, that means whenever I am getting there, that means it is affecting whenever I am adding with 2. So, at that time up to this it is basically changing its value. So, after that, for whenever I am that means adding with 8, then 16, then if I just add it with 32. Okay. So, that means at that time these bits are not affected by the corresponding addition of these 2. So, if I just want to conclude, or if I just want to that means observing the trends of changing of this position. So, at that time you find that here this corresponding, suppose if this is P 0, P 0 remains same for 2 to the power x plus 2. Okay. So, here if this is P 0 dashed, that is same as P 0. Then if you just follow P 1 dashed, if this is P 1. So, if you see that okay, this position was 0, now this becomes 0, this is 0, now it becomes 1. So, each of these bit position now will become 1. So, in the earlier case, whenever we are doing 2 to the power x plus 1, at that time what we have seen, that P 0 dash position, that was changing, sorry, yes, sorry, this is not this, that was P 0 bar. So, now here also you see this P 1 dash, that is nothing but just inversion of this particular position, which is P 1. Okay. So, that means now for this particular 2 to the power x plus 2, the P 0 dashed will be same as P 0, okay, and P 1 dashed, that will be P 1 bar here. Now, if I consider this P 2 dashed, so how it is changing from 2 to the power x? So, here also you see the same trend what we have followed or what we have observed in the 2 to the power x plus 1 case. So, in the 2 to the power x plus 1 case, what we have seen, that for this particular bit position if I consider, so initially there was 2 0, then there was 1, then rest of the bits was 0. So, here you see this is 0 and only this is there is 1 and otherwise it remain same. Okay. So, that means this is the carry which is generated for addition of 1 over here. Okay. So, that means now in case of, that means addition of 1, what we have write, that means on that particular case P 1 was the bit where P 1 was the XOR or with P 0 and P 1, that means where the carry is being, that means two adjacent LSB the bit position which is the last two LSB position, that were affected by addition of 1 there. So, here whenever I am adding 2, that means 2 means 1 0. So, now this one is basically affecting at the very next, it is starting from this P 1 position. Okay. So, otherwise the its remain same. So, that means at this case P2 dash can be written as P1 plus P2. Okay. So, now if I just draw the circuit, so at that time it will be something like, if I put x over here, so P0 is nothing but P0 here, and here this is P1 dashed, and if I just put one OR gate over here, so this is new P2 dashed, and this circuit is basically nothing but 2 to the power x plus 2. Okay. So, now next if I just ask you to design 2 to the power x plus 4 or 2 to the power x plus 8 or 2 to the power x plus 16, something like that, if I want to ask for, that means if I just ask you to design this, then what you can do? That means 4 means it will start affecting from the third bit P1 and P0. So, 4 means this is 1 0 0. So, as I am adding 0 0 to this particular bit position, that means these two will not be affected, it will start affecting P2 and P3. So, for 8, so that means this 3 bit position will not be affected, it will, sorry, this is P3, then P3 and P4 will be affected. If I added with 16, sorry, if I added with 16, so at that time up to P3 it will not touch, it will start affecting P4 and P5, something like this, it will start affecting. At which position I will just try to add this particular circuit will continue from that particular point or from that particular corresponding bit positions. Okay. So, now I can design any circuit something like this, which is 2 to the power x plus 2, 1, 2, 4, 8, 16, 32, any values I can do or I can implement by following the same trend. Okay. So, this is the design procedure of 2 to the power x plus 1 or 2 to the power x plus power of 2 value. It is not that if I want to add any other value, so at that time the design technique will be different. It is only applicable for if the value which I want to add, that is in the power of 2. Okay. So, if you want to add some different value, so at that time using this method or whatever technique I have followed to find out the logical expression, using that you have to find out and then you have to draw the corresponding architecture for that. Okay. Now, next if I want to implement another function, which is, let us consider another circuit which is y equals to 2 to the power x plus 1. Okay. So, y equals to 2 to the power x plus 1 if I want to design. So, at that time how it will look like. So, here you see 2 to the power x plus 1 means, so this x value is basically, this is x3, x2, x1 and x0, and if this is 2 to the power x plus 1, let us consider. Okay. So, this value is basically started from 0, but here instead of that, as I am adding along with this x plus 1, that means it will start from 1. So, initially what we are getting 2 to the power x, when we are finding this 2 to the power x, at that time 0 means this was starting from 1, because 2 to the power 0 means that is 1. But here what we are doing, in the next what was there, y equals to 2 to the power 1, that is equals to 2. So, 2 to the power 1, then 2, then 2 to the power 2, then 4, then 2 to the power 3, that is 8, something like this it was following. But so, as I am adding plus 1 over here, okay, so that means it will not, this 2 to the power 0, that we will not get. Okay, it will start from 2 to the power 1. So, that means here we will get 2, then we will get 4, for 1 we will get 4, for 2 we will get 8, for 3 we will get 16. So, that means now from this 2 to the power x block, how can we design this 2 to the power x plus 1? if I just draw this particular circuit, so if this is x, so at the time what it will be? That means for this initially there was this 1, so that position, if this is P0, then the P1, then P2, then P3, P4, something like this, if this was up to 15. Okay. So, in this case this P0 will not be connected. So, P1 will be connected, which will be P0 of this particular block, and P15, that will be P14. Okay. So, that means now I can, as I am considering, because here whenever for the final bit it will be, as I have just increased the power of 2. So, if I am considering fixed of 16 bit or 8 bit, so at that time I cannot hold the values of the maximum of x. So, that is why though for 2 to the power x I can hold the value of 2 to the P15, but 2 to the power x plus 1 I cannot hold the value within that bit position or within that word length. So, that is why up to P14 I can consider, and this will be the total block diagram of 2 to the power x plus 1. Okay. So, now the same thing, if I just using the same, that means now if I consider this y, suppose I have to add 2 to the power x plus 2, y equals to 2 to the power x plus 4, then how it will be, how can I design those circuit, that you can also try from this particular point. Okay. So, that I am not discussing over here. Okay. So, if you have doubt or how you can design, that we will discuss it in the forum, or we will discuss it in the offline. Okay. So, then next, suppose I want to design a circuit y equals to ceiling of log 2 base x. Okay. Suppose this function I need to implement. So, at that time if you just see, that means I need to do this ceiling, then I need to find out this log of this. So, how efficiently I can implement this particular function, or what will be the architecture for this log 2 base x ceiling of this. Okay. So, now we will see the corresponding circuit for that. Okay. Now, consider this x value. Now, for 0 to 1, what will be the corresponding log 2 x values? For 0 to 1, as we are considering this particular point. So, at that time, okay, so not this, first let me consider y equals to ceiling of log 2 x I need to implement, right. So, if I just draw something like this, x, the range of x will be 0 to 1, then 1 to, for 1 to 3, then then this is 2 to 3, then 4 to 7, then 8 to 15, then 16 to 31, then 32 to 63, then 64 to 127, then 128 to 255. Okay. If I am considering only the x bit x of 8 bit. So, now if I just consider this x, so that means x7, x6, x5, x4, x3, x2, x1 and x0. So, if I just write it something like this. For any value of that is 0 or 1, that may be 0 to 1 range, means that will be 0 or 1. Okay. So, for that what will be the, so in this case, sorry, y2, y1, y0, it will be 0 0 0. So, as this is that means this is the function 8 bit I am considering. So, log 2 base x means that can be covered within this 3 bit position. Okay. Then what I need? For 1 this, that means 2 and 3 means this is 1 and then this position will be 0 for 2, 1 for 3. Okay. So, whatever is the value of this, that does not affect. If this is 1, so at that time it will be 1. So, 4 to 7 means the range is basically from 0 0 4, then 5, then 6, then 7. I can implement or I can write this particular range in this manner. Then for 8 to 15 range, how can I write? This will be 3. In this same manner, if I just write it for, it will be 4 for this, say 32 to 63, the range will be something like this, and for that I can write this as a 5. For this, sorry, so it will be 6, and for this particular point it will be 7. Okay. So, that means for any values within the range of 0 to 1, this ceiling of this log 2 base x, that will be 0, then this will be 1, then this will be 2, then 3, 4, 5, 6, 7, as I am considering 8 bit of x. So, now from this particular operation table, can I conclude that what will be the circuit for this particular table? So, if you see, this is nothing but a priority encoder circuit. Okay. So, that means priority encoder means in digital encoder, how it will be? That means for 0 0, for suppose 4 bit, if I just consider. Okay. So, at the time how it will look like? That means for y0, y3, y2, that means at the time each of this bit for each of this bit position, how this the corresponding output bit varies, so that we encode. Okay. But here, that means for decoder circuit, what was that? That 4 to 16. In encoder, how it will be? It will encode from 16 to 4. Okay. Now, but here the thing is that whenever this bit position is 1, no matter it depends on the other values. Okay. So, if I find this bit position as 1, so at that point this will become 1. So, no matter what is the value of this 2 particular bit position, if this bit position is x2 bit position is 1, at that time the corresponding encoded value will be 2. So, from this particular table you can see as this at this particular point x7 value is 1, no matter what is the value of others these bits, it will corresponds to this 111 or 7. Okay. So, for this is, if I just consider this particular operation table, it is same as the priority encoder circuit. Okay. So, priority encoder circuit means now this log2 base x function that can be implemented using this particular function that can be implemented using one particular priority encoder circuit. Now, the thing is that now I have to derive or I have to draw the architecture of priority encoder circuit. So, from this particular table if I just observe, and after observing what I have to do, I have to find out the logical expression for each of this particular bit position, that we have to find out, and after finding out those logical expression will be converted or that will be that means implemented via logic gates, that we will see. Okay. So, that we will be see in the next class. Thank you for today's class.